Yeah, welcome to the second lecture of scanning probe microscopy. Now I have created here what I will be using for demonstrating the atomic force microscopy. This will be my scanning tip, the cantilever that is. I'm wondering how that will work. I told you in the first lecture that the main drawback with the scanning tunneling microscope is that it needs to have electric conducting surfaces. And of course you want to investigate more than metals and semiconductors and things like that, so then you need to invent something else. And that's where this atomic force microscope comes into the picture. You remember from the scanning tunneling microscope lecture that these microscopes works like that. You use a probe that scans across the surface and maps off the topography. Sort of like a finger that you senses it like this. In atomic force microscopy, you have invented a key idea that you have used is that you can measure the force between the tip and the surface. In the tunneling microscope, you just measure this electric tunneling current, and that sort of gives indirectly a way to measure distances. But if you instead can measure forces, the interacting forces between the tip and the surface, then you're sort of free and doesn't need to use metallic surfaces, because you don't any longer need to have an electric current. And that's where this cantilever comes into the picture. You know that if you have a cantilever like this plastic piece here, you can design those so that you know that the spring constant of it. You know what material it is made of, and you know the physical dimension of it. And then you also know the spring constant of it and the force that is required to bend this. If you use that idea and design a very, very small tip, not as I have here, but you made it, for example, out of silicon with the silicon technology. And in the demonstration I've showed you a few of those. And then you can create a small tip with a known spring constant. And then when you use that small tip and scan the surface, you can take some obstacles again for that. Take this pile of paper. When the tip comes here and comes and scans across the surface, it senses we have a force between here, because it is something solid that is gone, right? When it comes here, it will deflect like this, right? And then it goes down. It will be loosen its tension again here, right? So this is the main idea in atomic force microscope. When you scan the surface, this tip will deflect up like this when it goes over, and if you can measure this deflection of this cantilever, then you know the forces that is required when you go over the obstacles. And then you can use the same kind of control feedback loop as in the scanning tunneling microscope. So when I scan over this surface like this, here, the forces will be high when the tip goes up, and then I can use the control unit to regulate and compensate, so it loses the tension of the spring like this. And that means when I scan here, I can keep the bottle as close as possible to the obstacles and follows the contours. Because as soon as I get into some obstacles, the tip will deflect up, and I will measure this change in deflection of the tip, and then I can compensate by raising the tip up from the sample, and if the tip is raising too much, it will deflect in the opposite way. So then I can keep this at a constant position while I scan. So that is the main idea with atomic force microscope. You measure the forces that interact with the tip and between the tip and the sample. And a way to measure that is to use something with a known force and measure the relative change of that. So here we use the cantilever. Now comes the problem. How do you measure the deflection of a tip? I mean, in this case, it's easy, we see the deflection. But in the tips that use in atomic force microscopy, the tips is very small and the deflections are very, very little. So how do you measure that? Well, one very common way is to use lasers. You make this top surface of the tip mirror-like. So you put a reflective coating on top of here. You shine a laser down here and up to a sensor that you have here. Then you will see when the tip deflects up like this, it will change the angle of the surface. That means that the laser will take a different trajectory if we change the angle of this mirror. And that means that the distance on this sensor on this side will be, the location of the laser on this sensor side here will be at a different position if this deflects. And then that change in location will be directly proportional to the force on the cantilever. So then we can measure the force. So in atomic force microscopy, you have this laser geometry set up that measures the deflection of the tip when you scan. So then you know how to measure the forces with the machine. Now there are a little bit different ways that you can approach this. I mean, the basic thing, as I said, is you just scan the surface like this, and when this deflects up, it changes the angle, the position on the sensor, and then you compensate for that, and then you can scan across. It bends down when you come over the hill here, and then we compensate and put the tip down and scan. The problem arises when, let's say I change the viewing direction for you, and then we view the tip from this way when I scan. And here I scan, and then I come to the object, and then the tip will bend like this a little. So we will have some kind of torsion motion here. And then when it comes over, it snaps back and goes back down. And this is very clearly seen if the sample is sticky and not very hard. Then the tip will have these friction forces against the surface while it scans. And that is a problem, because if you have this friction thing in the surface, then the tip can start to vibrate. Due to this, you have a constantly static and gliding friction of the tip. And that will create a very noisy image for you. So basically, it is very hard to use this technique to scan soft materials, biological things, for example. So then one invented as an approach to conquer this problem, and that is you can use, instead of having this constant, this contact mode approach, as it is called, when we are in contact with the surface. One started to use what's called dynamic mode, and in dynamic mode there is several different approaches, but the main idea is to sort of try to eliminate the problem of this dragging across the surface. And the first approach to that was to use tapping mode, and in tapping mode you do like this. So then you avoid, when you scan the surface, you don't have this dragging friction on the surface. Instead you tap like this and measures the chains of that. So that is sort of a halfway progress to what's called a non-contact mode. This tapping mode is very easy. Most machines can do that, and it improves the resolutions very much. Of course, there is perhaps some cases where you actually want to measure the friction on the surface, and if you have some non-homogenic material with different regions of this, then it can be interesting to see which regions have more and less friction. So that can be an investigation by itself, but usually friction is a problem. The final approach in this invention of these techniques is called the non-contact mode. And in the non-contact mode, you don't have any contact with the substrate at all. Instead, you have the tip vibrating like this. So when the tip is vibrating, it has a specific resonance frequency like this. And the idea here is that if you have something that's close here, then you will have atomic force interaction between this vibrating tip and the substrate. And that force will have a damping effect on this cantilever. And then you will get a different resonance system, and that means that the resonance frequency of this will shift. And if you can measure the resonance frequency of your cantilever, then you have another way to measure the interaction of these atomic forces, right? So in non-contact mode, you have this vibrating tip that goes above the surface like this. And when it comes over close to obstacle, the resonance frequency will I don't know, it's hard to change that, but I can hold it closer. Then the resonance frequency will increase like this due to this interaction forces. And when I come down out in the opening here, it will go back down again. So that is how you do when you use this non-contact mode. I think these few techniques that I showed you now, it sort of gives you the most general idea behind this.